Jeff and I will talk about like a project I've been working on for quite a long time, which is not at Keep 848 in Apache Kafka, which is basically the next generation of the consumer relevant protocol. And in this talk, we will focus on some of the benchmarks that we have run to basically verify that it performs better than the old one. So I'm David.
I'm Jeff.
So here's the agenda. So I will do like the first half of the presentation, and Jeff will take it over. So my goal is to basically go through 3 items. So first, I would like to introduce the old and the new Rebalance protocol to basically give you enough information to understand what Jeff will be presenting afterwards. And then we have 2 topics about what is coming in Apache 4.0 about the group coordinator and the consumer. Then Jeff will take it over to talk about like all the benchmarks we have run to verify the performance of the protocol. He will do like a demo to compare the old and the new protocol, discuss some trade-offs, and then we will finish with like what are the next steps for the project. So let's start with really the basics. Why do we need like the Rebalance protocol in the first place? So let's say that you have a cluster with like a topic, full with 3 partitions. And then you have like 2 consumers that you want to use to basically consume all the messages from those topics. You basically need the mechanism to assign those partitions to those members, right? In order for them to consume. And this is where the Rebalance protocol basically kicks in, right? This is basically a protocol used by the consumers to let them agree on who should do what in the group and who should be consuming from which partition. So in this case, consumer 1 might be consuming from partition 0, and consumer 2 from partition 1 and 2, right? And then you can have like multiple consumer groups running in parallel with different topology. So until today in Apache Kafka, we have what we call the classic Rebalance protocol. That's a name we gave it to it like pretty recently, actually. Before that, it was known as a Rebalance protocol. And that one has a pretty interesting design. Back in the days when we designed it, our goal was to make it really generic, such that we could use it to assign any kind of resources. For instance, in Apache Kafka today, we use it to assign partitions, for consumers, but Connect also use it to assign tasks, for instance. So that was an interesting design choice, which basically led to really splitting the responsibility between the server and the client. So the server in this protocol basically just do membership, who is in the group, ensuring they are alive and such things. And then on the client side, they have to provide like the resource definition, and they have to handle like all the assignments of the group. Another thing is like this protocol is known also for having like what we call like a synchronization barrier, which basically block the group for all the members. On the other hand, for the new protocol, we basically started from scratch. And we basically decided to go the other way around. So we have basically designed a protocol which is really tailored for the consumer, and that's it. Which basically means that one of the goals we had was to really move like all the responsibilities from the client to the server. So in this new protocol, the server has to manage membership as the old one, but it also manages like all the resources, who should consume what and when. And a good thing is that this protocol is basically incremental, versus having like this synchronization barrier for the old one. So I would like to briefly introduce like the 2 protocols so that you basically understand how they work from a high-level perspective. And for that, I will use like a simple example. So here we basically have like 3 consumers, A, B, and C, where A has like 2 partitions, 1 and 3. B has like a single partition 2. And on the bottom, we have the coordinator, which is basically the service running on the server, providing like the Rebalance protocol. So let's run the old protocol to start with. So the first thing is that in our protocol, we have like 3 FPCs involved like in any rebalances. We have like a heartbeat to basically maintain the session with a group coordinator. We have a join group RPC and a sync group RPC. So let's start with a group in a steady state. So in a steady state, they basically heartbeat to the group coordinator to maintain the session. And when C joins, it will send a join group request to the group coordinator. And at this point on the server, we basically start the rebalance process to reassign the partition. So when A heartbeat next, he will basically learn that the rebalance is ongoing, and he will join the group again. When B heartbeat, it will also learn that there is a rebalance, and he will join a group again. And it's only at this time, when all the members have rejoined, that the group coordinator will basically reply to anyone and also designate like a leader to compute the assignment on the client side, right? And this is where this synchronization barrier basically is, because we have to wait on all the members of the group to rejoin in order to proceed. So here we have 3, it's pretty simple, but imagine if you have 1,000, it might take some time, right? So at this point, the leader and all the members will send like a sync group request to the group coordinator, and the leader will basically provide the assignment for the group. Then the coordinator will reply to all the members with basically their assignments. And in this case, the assignment will basically tell to member A to revoke the partition tree. When the revocation is done, the member A will trigger like another rebalance to basically reassign this partition. So it will join the group. A will discover, A and B will discover that there is a rebalance. They will rejoin the group again. We wait on all of them. We go back to the leader to compute a new assignment. Then the leader sends the assignment to the coordinator. We distribute it to the member. And finally, partition tree is reassigned to member C, right? So it basically takes like a lot of chit-chat and a lot of interaction between the client and server to get there. Let's look at the new protocol now. So in this case, we went really simple. We have one RPC, which is called the consumer group heartbeat RPC. So in the steady state, member just heartbeat with this RPC, and when the member joins, he sends like a heartbeat to the member to basically say, hey, I'm here. When it does, the coordinator will compute a new assignment on the server side for the group, and then reply to C with basically nothing, because there is nothing he can do at this point. When A sends the next heartbeat, the group coordinator will basically tell him, hey, you have to revoke partition tree now because you're no longer assigned to it. So A will proceed and do the revocation. For B, this rebalance has basically no incidence because there are no changes for him. For C, he still has to wait because there is nothing he can do. At some point, eventually, A will use like one of the next heartbeat to say, hey, now I'm done with the revocation. So at this point, the coordinator will persist that the fact that the partition is not available for other members. So for B, still no changes. And when C heartbeat next, the coordinator will basically tell him that he can use partition tree now, right? So it basically take like a few round trip of heartbeats, but only one RPC and no synchronization, except the fact that the coordinator had to synchronize the two members between themselves, right? But in this case, B, for instance, was not impacted at all, right? So it's much simpler on the client side, and it's much simpler to understand. So now I would like to say a few words about the group coordinator. So unfortunately, we don't really have the time to go really in deep details for that. But the thing I would like to say is that we have completely rewritten this service on the broker side, and we will really ship like a fully rewritten implementation in AK 4.0. It's fully backward compatible, and it basically provides like the classic protocol and the new consumer rebalance protocol. The new architecture is based like on an event-driven architecture or like an event loop style architecture. And there is one thing to know, which is really important when you upgrade, is that it basically runs in a new thread pool in Apache Kafka. So you have to be aware of this new setting, group.coordinator.thread, which default to 1. So if you upgrade to 4.0, you may have to tweak this to use what is appropriate for your workload. On the consumer side, we are also shipping like a brand new consumer in 4.0. It's basically the same. We still implement the same interface, and we support like all the features, but it's also based on a new threading model. So in the implementation we have today, you may know that everything runs in the application thread. So when you call like consumer.poll, it basically triggers interaction in the background. In the new model, we have basically decided to use like a background thread to run all the IOs and all the interaction with the server. There is also like a setting for that called group.protocol, and the new model is only used if you set it to consumer, and that will be the default in 4.0. There is one thing to know. In the new protocol, we don't support clients and assigner anymore, at least not now. It might come in in a future release. And that's it for my part. Over to you, Jeff.
Thanks, David. Can you hear me? Okay. All right, so in the following slides, I'll talk about the performance of the new coordinator, the Rebalance protocol, show a demo of it, and discuss some trade-offs. So for the new coordinator benchmarks, our main goal was to ensure that we didn't introduce any regressions. And we observed several metrics, but the two metrics we'll focus on this presentation is the offset commit total time and the CPU. The offset commit total time will help us understand the efficiency of the write path, which includes time to replicate partitions and records. And we chose the CPU as an overall indicator of the broker health when it's under stress. The two load dimensions that we'll focus on is the number of members. If the number of members increase, it'll add more work to the coordinator, and we'll also stress the offset commit request rate to put pressure in the write path. The numbers we chose for the setup were based on our observations from clusters in production. So here's our setup. We had a single topic with 1,000 partitions and 4,000 members distributed evenly across 40 groups. We used 2 consumer offset partitions and reassigned them to a single broker. And the process was we would ramp up the consumers, and they would consume for 1 hour, and we would close the consumers. And here's the results. So this is the graph of the offset commit total time, and the peaks and troughs of the old coordinator are roughly peaks and troughs of the old coordinator are roughly 2 times slower compared to the new coordinator. And I know you can't see closely in the graphs, but during steady state, the old coordinator averages roughly around 250 milliseconds, whereas in the new coordinator, it averages around 125 milliseconds, which is a pretty great improvement. And this is the graph for the server load. The CPU load is more or less the same. We see a minor improvement, but we ensure that there are no regressions here. We conducted additional tests by stressing different load dimensions. We increased the number of members, the number of groups. We also increased the offset commit request rate. And through these benchmarks, we confirmed the new coordinator not only avoids regressions, but is more performant in most scenarios. And now let's look into the Rebalance protocol benchmarks. So how do we measure the impact of a rebalance? During a rebalance, some or all consumers need to revoke partitions and need to wait for partitions to be reassigned. And during this time, they cannot commit offsets, which impacts read availability for the consumer group. So we looked at the fetch throughput stability during a rebalance to measure the impact. This is the setup for the benchmark. We produced 29 megabytes per second of steady produce to the topic with 2,000 partitions. And we started 1,000 members, where each member would be assigned 2 partitions. And once the group stabilized, we performed a rolling restart. We compared against 3 different assignment strategies, the first 2 being from the existing rebalance protocol with different variations, and the last one would be the new consumer rebalance protocol. And these are the results. At the top, you'll see the eager assignment strategy used. And you can clearly see that the egress is very unstable. And the initial decline in egress can be contributed to the fact that during an eager rebalance, all consumers must revoke all of their partitions. And the spike in egress would represent when the consumers have reassigned partitions and trying to play catch up to the high watermark. On the other hand, the cooperative and consumer rebalances are pretty stable. The peaks and troughs are quite close to the expected egress of 29 megabytes per second. But we do see a minor improvement in the consumer protocol. So if we look at this, we can say that we do understand that cooperative rebalance is also very effective, but it has a key weakness that all consumers must be very responsive. And if one or more consumers are slow, then basically the cooperative rebalance will suffer. So to provide this scenario, we also had a similar setup as before. But instead of having 1,000 fast members, we introduced slow members, where we introduced a 10-second artificial delay whenever partitions are revoked or reassigned to these members. And these are the results with slow members. The cooperative rebalance also shows a similar trend as we saw before in the previous benchmark with the eager rebalance. Whereas the consumer protocol is very stable throughout the rebalance. So one might ask, what if only a single member is slow? And this would be more a realistic in a real-world application. So to demonstrate how the new protocol will behave, let's do a demo. So at the top A, we have a single craft node running locally. And we'll use the left 3 panes to use as a classic group using the cooperative assignment strategy. And on the right, we'll use these 3 panes to create a consumer group with 3 members. And for the slow member, we'll use the first member of each group. This delay of 20 seconds is basically the delay that we introduced in the previous benchmark. So let's start the first members. We'll have to wait 20 seconds before partitions are actually assigned to them. And this demo topic that we're using has a total of 6 partitions. So we see partitions 0 through 5 being assigned to both members. Okay, so now we'll start the second members. At this point, we don't expect much difference because both members have to wait for the slow member to revoke 3 of their partitions, which in this case would be partitions 3, 4, 5. So partitions 3, 4, 5 revoked and assigned, revoked and assigned. Okay, great. So right now, to recap, we have the first member have partitions 0, 1, 2 assigned, and then the second member has 3, 4, 5 assigned. And this is identical for both groups. So this is where it gets a bit different. Notice the time when we start the third member, when the partition 5 is being revoked from the second member and when it's being assigned to the third member of each group. So I'm going to start them together. So they are revoked immediately. And in the next heartbeat, the consumer group member is able to consume from partition 5 immediately. Whereas in the classic group, the member still has to wait for the first member to revoke their partitions. We see them being assigned here, and we'll see being assigned here. So this demo demonstrates that the new rebalance protocol is truly incremental. And if you imagine a scenario where this group and the number of members scale to 1,000 members, and during a very high throughput workload, then you'll be able to understand that the rebalance protocol has a much higher read availability. Going back to the presentation. So we've confirmed the benefits of the new rebalance protocol, but there are some trade-offs. The first is the CPU implications during rebalances. So now the consumer is responsible for computing these assignments, and there's more work for the coordinator to compute them. Also, during a rebalance, the coordinator also has to do more work to reconcile each member to their desired assignment. Furthermore, consumers have more frequent heartbeats during rebalances because they want to reconcile to their assignment as soon as they can. To demonstrate the CPU load, we used a similar setup that we used before. And this is the CPU load during a rebalance. The actual numbers aren't that important, but just notice the general trend where in the cooperative rebalance, the CPU decreases, whereas in the consumer rebalance, the CPU increases. The second trade-off is the increase in memory footprint. As the server is responsible for computing these assignments, they have more data to store, for instance, the group assignment, as well as other data structures to make the assignment computation more efficient. There's also a difference between how we store each assignment for each member. This is a heap dump that we took for a group that's subscribed to 2,000 partitions. In a single member, the classic group member stores 500 bytes, and in the consumer member stores 1,000 bytes, which is almost a 2x increase. And in a group with 500 members, we see the classic group holds 300 kilobytes of data, whereas the consumer group holds 800 kilobytes. So there is a substantial increase in memory that we use. To recap, we confirmed that the coordinator did not introduce performance regressions, and in most cases were more performant. We also confirmed that the consumer rebalance protocol shows great stability during rebalances. And through the demo, we confirmed that the protocol is truly incremental. We also covered the trade-offs that we made, where the coordinator load increases during rebalances, and that we have a larger footprint, memory footprint. So what's next? We'll be planning to ship the consumer rebalance protocol, the new group coordinator, and the new asynchronous consumer in Apache Kafka 4.0. It is missing some features, like KIP 881, which is the rack-aware partition assignment. So at the moment, the server is unable to compute assignments based on the partition racks and the client racks. Also, as David mentioned, it is not able to support the client-side assigners yet. And for future work, we have KIP 1071, where the community is working to bring all of the benefits of the consumer rebalance protocol to streams and make streams initialization and task assignments a first-class citizen in the Kafka protocol. And that wraps up our presentation. Thank you.